Okay, this is problem 2.3 of Griffiths quantum mechanics. So this is the first problem regarding the infinite square well. So the infinite square well looks like this, where we have our x, and say we have some potential v, that's a function of x clearly, and the sides of this are such that the potential is infinity at these points. And these points are at 0 and at a. That's the width of our square well. Problem 2.3 is to show that there is no acceptable solution to the time-independent Schrödinger equation. Our time-independent Schrödinger being this guy, h bar squared over 2m, the second spatial derivative of our wave function, plus the potential times the wave function equals the energy. More commonly written this way. I'm going to go ahead and group those over on one side just to be a little bit more clear. So I'm just going to have this derivative on one side, and then I have a, I want v minus e. We could go like this, or we could do it this way too, depending on where you like your negative. Either way works just fine. Okay, what we want to do is show that there's no valid solution if our energy level is, say, here. So we can't have an energy level that's below our square well. This is to show that the only valid energy levels could be up here, inside the well. Analogously, this is kind of like problem 2.2, like kicking the ball, going up the hill, showing that the energy level has to be up here. It can't be below the potential energy line. If we were to draw that in an energy landscape sort of graph. So inside the square well, our potential equals 0. And for this problem, let's do it where E equals 0. So that means that we have h bar squared over 2m d psi dx squared equals just 0. 0 minus 0 is 0. 0 times psi is, of course, 0. I can simplify that up by multiplying both sides by 2m over h bar squared, and what I get is that the second derivative of psi with respect to x is 0, meaning that if I were to graph out psi of x, I have a straight line. This will correspond to a constant or a linear function. So the short answer to this is that the energy cannot be 0 because that would make our wave function a linear function. So this is not a wave. It is a constant or it is a linear function. Those are the only two options that would give us a second derivative equal to 0. So that takes care of why it can't be 0, which is nice. So that one's pretty easy. That's pretty straightforward. Like I said, in short, it just flat out isn't a wave. If we want to go out a little bit further, if you want a little bit more mathematical justification, let's look at the boundary conditions. So our boundary conditions, this will tell us exactly what it is. Our boundary conditions is that psi of 0 must be 0, and psi of A must be 0. And that's because outside our potential well, the wave function doesn't exist. It is equal to 0 over here and over here, and our wave function has to be continuous. So it has to equal at these boundary points. That means that inside the well, the only way to satisfy this equals 0. Let's say we made that some, psi equals a linear function, mx plus b, giving us d psi dx equal to just m, and our second derivative equal to 0. So it satisfies our differential equation. In order to satisfy our boundary conditions, then we have to have psi of 0 equals 0, making mx, x is 0, plus b equals 0. So that means our intercept is 0. And then psi of A equals 0 as well, meaning m times A plus 0 equals 0, meaning that our slope is also going to be just 0. So if our intercept is 0 and our slope is 0, then that means psi is a constant 0. So it's not a solution because it just doesn't exist. Psi doesn't exist outside the well, nor does it exist inside the well. So E equals 0 is flat out not a solution. E equals 0, not allowed. That does not allow for, say, a trapped state. A quantum particle cannot exist trapped in a well if there is 0 energy. Now for E less than 0, let's go ahead and write out this guy again. So here's my time-independent Schrödinger equation. My potential inside the well is equal to 0. So then I have E times psi, but E is less than 0, so E is negative. I can go ahead and just get rid of both negatives now. And I have this function. Now, the deal with this is that if I have psi equal to, say, either a sine or a cosine, right? Then I have d psi dx. that equals cosine. And then the second derivative, we get that negative sign out there. So in order for it to be this sort of wave, we have to have that negative sign out there. If the left-hand side and the right-hand side both have the same sign, then that means that we're dealing with an exponential. That means we're dealing something that looks like, let's say, e to the kx. We could say a times e to the kx plus b times e to the negative kx. So then when we take the derivative of that, we get a k e to the kx plus negative b k e to the negative kx. But then when we take our second derivative, we get the same sign that we started with. The exponential increase is a little more obvious. Then we get negative bk times negative k. So then we get the positive out there again. So what that means is that for this equation, instead of getting a sine wave or a cosine wave, which really only just depends on your boundary conditions, instead now we're getting some sign that has this form. And we can always have some constant out there. A and B would just be normalization constants. What's the problem with that? Problem with that is boundary conditions. And this one, you don't even have to plug it in. You certainly can. But you can also just look at it graphically. I mean, in this case, we have either a exponential increase we could have something like this, or we could have an exponential decrease. Or exponential decay would probably be a better way to say that. Either way, we don't have this bending around so that it comes back to the same value. We either have an exponential increase that diverges, or we have an exponential decay, which also diverges. Just one diverges at positive infinity, the other diverges at negative infinity. So, meaning if I were to take psi of 0 equals 0 first, then I have a of k times 0. So that would be k times 0. That's e to the 0. Plus b negative k to the 0. And that gets me that I either have A equal to 0, B equal to 0, meaning my wave function is just 0. I could also do this one first, but I have the same exact problem. Here, you could sort of maybe justify it a little bit. I could have, if A is positive, I could argue little a is positive. I have to have this case here. A has to be equal to 0, my normalization constant, A equal to 0. It can only be an exponential decay if and only if A were going to infinity. But that's not the case here. So that means we cannot have the energy less than 0 in an infinite square well. There are other cases we can have this. Or if A were equal to negative infinity, we could have an exponential increase. It's valid, just not in an infinite square well. Infinite square well. And there we go. There's our full solution out there. And that is problem 2.3.